everyone, today we are going to talk about the remaining part of general organic chemistry. Today is one of those important parts because we are going to discuss about reaction mechanisms. Right? We already talked about basics of organic chemistry, what are the intermediate present and how the questions can be asked from the intermediate part. And then we talked about electronic effects like hyperconjugation, inductive effect, resonance effect, and electromagnetic effect, and how it is affecting the intermediate stability and etc. Today we are jumping into reaction mechanism. How the organic reaction happens. If you take any reaction, it follows basically these three types of reactions: substitution, elimination, and addition. We are going to see in detail about these three reactions. I'm sure in the end of the session, you'll be master in organic chemistry reaction mechanisms. So without any further delay, let's get started. First, we are going to talk about substitution reaction. What is substitution? Substitution is nothing but the replacement. More technically, if I want to speak, then the substitution reaction is in which the functional group of one chemical compound is getting substituted by the another group or replaced by the another atom. Those are called the substitution reactions. Say for example, if I am having ROH, I am using HX. As the end product, I am getting RX plus H2. What happened over here? OH is replaced by RX. So that is substitution reaction. Here we have two types of substitution reactions. One is electrophilic substitution reaction, and the second one is nucleophilic substitution reaction. Electrophile, nucleophile. What is the difference? Electrophiles are the one which are electron loving species, and the nucleophiles are electron hating species. Out of these two, today we are going to see in detail about nucleophilic substitution reaction. Why only that? Because electrophilic substitution reaction, we are going to see that in haloalkanes chapter in detail. Now let's see about nucleophilic substitution reaction. What is nucleophile? Electron loving species. Okay, so how we can identify that? How it will be present? By seeing any molecule or an atom, how I'll get to conclude that is a nucleophile. Yes, you can do that, because nucleophiles are the one are ready to share its electrons. They are electron hating, correct? So usually that will have unshared electron pairs. For example, ammonia, which is having a lone pair in it, correct? So Lewis bases or the nucleophiles. Any other nucleophile we are encountering in reaction mechanism? Yes. The nucleophiles are there of three types. The first type is negatively charged. Of course it would be negatively charged because they are electron rich. So for example, you can take OH minus, Cn minus. These are some famous nucleophiles. Of course are halo groups, Cl minus, F minus, I minus, Br minus, and etc. Apart from that, we have NO3 minus, SH, thiol group SH minus, or RCOO minus, OR minus, sometimes H minus, hydrate as well. We will see more reactions about that. And the second type is that all Lewis bases, which are containing one lone pairs. For example, RMGX, RLI, or lithium aluminum hydride, R2ZN, or organometallic compounds are considered Lewis bases of nucleophile. How, ma'am, how these are having electrons to be donated? How it can act as a nucleophile? Yes, you can see, I told you these are metals, right? Metals are electropositive. So obviously these alkyl groups will become negative. So these becomes the electron donors. Okay. The third type, that is ambidentate nucleophile. What is that? Ambidentate, we talked about that. Those are flexible. Here the ambident nucleophile are the one which are having two sides of electron-rich center. Is it possible? Yes, it is. Two sides of electron-rich. Say for example, I am having Cn minus. Okay. So here carbon which is having negative charge and the nitrogen that is having lone pair. So this side also it can act as a nucleophile and this side also it can act as a nucleophile. One, if that is attached with carbon, then the product will be cyanide, and if that is attached with nitrogen, then the product formation will be isocyanate. So there are this kind of ambident nucleophiles are also exist. NH2OH or nitro group which are having both the sides attack. Okay, so we talked about nucleophiles. What about their mechanism? In nucleophile substitution reaction, we have three different types of mechanism. These are important I am talking about. They have many: SN1, SN2 and SNAR. What is SN1? As the name indicates, S stands for substitution, N stands for nucleophilic, and Y1 stands for unimolecular. What is unimolecular? We talked about the rate of the reaction, right? In chemical kinetics, rate of the reaction. In SN1 reaction, the rate of the reaction is 1, because in the rate determining step, only one reactant is responsible for finding the rate. Let's go in detail. This type of mechanism follows two steps. Step 1 is formation of carbocation. Step 2 is attack of nucleophile. We know about carbocation very well from our last video. Now, let's go step by step. First, let's talk about the step 1. Formation of carbocation. Right. So let me take a carbon which is having the 3 substitutions. Okay, so let's say this is OH and this will be getting replaced. So on the side I'm having RRH. Okay, so the first step, that is rate determining step. Why that is rate determining step? Because that is a slow step. So carbocation formation will lead to a carbon structure like this, isn't it? So remaining OH left the compound. Okay. As a second step, we know that is a attack of nucleophile. So I'm taking the same carbocation which is having a empty orbital. So let me write it. Empty orbital like this. So what can happen over here? That is more important in case of stereochemistry part. So what can happen? The incoming nucleophile can attack on both the sides. It can attack left side or it can attack right. Okay, so it can go about attacking this empty orbital, or it can go by attacking the another empty orbital. So what kind of products we can expect? So one thing, if that is attacking to the left, the product would be like this. That's it. So if that is attacking on away from that another low, then the product is like this. What about if that is attacking on this side, right side? Then the product becomes like this. So this is on right and that is on left. So what would be our product? What would be our end product? Here the twist is these are enantiomers. So both the side attack can be happen. That's why one is retention in configuration, another one becomes inversion in configuration. Overall, it can form a racemic mixture out of this. Okay. So it's depend on which side the attack is happening, which side is favorable for the given substrate. Okay. So that is about the stereochemistry of SN1 mechanism. And talking about the kinetics part, the rate is proportional towards Rx, the substrate, the reactant we just took. So the rate is equal to like this. So the energy profile diagram for SN1 becomes, I'm writing it versus energy to reaction coordinate. So it will start, the reactant will start and reaches a transition state and an intermediate and again a transition state to give the product. Right? So this intermediate, that is carbocation intermediate, this is transition state 1 and this is transition state 2. Transition states are very short-lived when we are compared to the intermediates. Okay, this is also important. So what are the factors can affect SN1 reaction mechanism? The first factor is, of course, nature of alkyl group. Because you have to remember one thing, the carbocation formation step is very important in this mechanism. So stability of the carbocation determines the rate of the reaction. So tertiary carbocation is more favorable, then secondary, then comes primary, then methyl. Okay, so you have to take care of that. And the second thing is nature of leaving group. Nature of leaving group. So here you have to consider the size of halogens which are leaving the group. For example, here if I am talking about RF, RCl, RBr and Ri, so the leaving capacity is more for I, then comes Br, then comes Cl and then finally F. Okay. If the acidic strength is more, then the leaving capacity is also becomes more. Weaker the base, more the leaving capacity. And most importantly, the third point is nature of solvent. How solvent presence is taking a huge role. Here you have to consider only the polar protic solvent. So which facilitates the carbocation formation very easily. How it becomes? Because it can form a bond with our leaving group and then it leaves eventually. And the concentration of nucleophile. Some questions can be asked from this part. What will happen if I am changing the concentration of the nucleophile? It will not affect the rate of the reaction. So the rate is independent of concentration of nucleophile. Why? Because it is not taking part in the rate determining step. Okay, so these are important in case of SN1. If I am going to talk about SN2, you must be aware of SN1. Because it is just opposite. SN2, that is bimolecular, and it follows a single step mechanism. How it give product? Let's see. For example, here I am taking CH3CH2OH reacting with HX. It is giving us CH3CH2X along with H2O. Okay, so how the mechanism follows? So let me take the same compound, CH3, H and another H. Okay. First it will form, the nucleophile will get attack on which side? In the SN1, we talked about it can attack from either of the side, depend on that the product formation will be there. But here there is no opportunity to attack it from leaving group side. It have to attack it by opposite side. Correct. So in that case, it will form a intermediate like this. We can say it intermediate. That is just a transition state it is forming, where leaving group is about to leave and nucleophile just got attached to the carbon. Followed by the elimination of leaving group happens. The molecule will look like this. Due to the attack of opposite side, it always goes with inversion in configuration. Inversion in configuration means if one reactant is S configuration, the product will be R. Okay, so that here the Walden inversion takes place. We are not going to talk much about Walden inversion. Again, the rate of the reaction is depend on both nucleophile as well as a reacting substance, so that the order will be 2, which becomes this is bimolecular reaction. What are the factors affecting over here? The first factor, that is nature of alkyl group. We already talked about that. Here the alkyl carbocation formation is not important, so it takes where methyl comes first and then primary, secondary and tertiary. So if that is tertiary is mostly favored by SN1 instead of SN2. So why this is happening like this? Because due to the bulky group present in tertiary, which happens to the steric hindrance, so nucleophile can't attack if already the group is bulky. So the rate decreases. The second part, that is nature of leaving group. Nature of leaving group, once again, weaker the base, more will be our leaving group capacity. Same as SN1. And the third thing is effect of solvent. Solvent effect. Here, polar aprotic solvent. Difference between protic and aprotic is that in case of protic solvent, hydrogen will be present. For example, water, alcohol, like that. Here, polar aprotic solvent is most favorable, where the hydrogen is not taking part much. For example, for aprotic solvent is DMSO, DMF, acetone. So these are some polar aprotic solvent. So if I want to write the energy diagram of SN2 reaction, then the reactant starts and then it reaches the product with the only one transition state. It's same as the versus energy versus coordinate reaction coordinate. The energy diagram goes like this. Reactant reaches one transition state, leads to the product. But in case of SN2, it reaches two transition state along with one intermediate formation. Okay, so this is about SN1 and SN2 reactions. So what about SNAR? AR here stands for aromatic. So aromatic groups can't undergo SN1 and SN2 mechanisms because of the partial double bond formation, which is more important question. So it undergoes SNAR, which is also called as elimination addition or addition elimination mechanism. Say for example, there are certain conditions for the benzene group to follow SNAR mechanism, that is, it should have a strong electron withdrawing group. So the electron withdrawing group facilitates the leaving group to leave the compound. So nucleophilic attack happens like that. Due to that, it will form a product. It's not a product, it's the intermediate like this. More precisely, so again it undergoes the resonance because of electron withdrawing group. So minus charge comes here. And once again the minus charge moves to the another ortho position. So finally the leaving group leaves. Like this, and then the nucleophile will occupies that position like this. So this is aromatic nucleophilic substitution reactions. So if that needs to happen, there should be a strong electron withdrawing group at ortho or para positions to the leaving group, so that the resonance will get stabilized. If that is present in meta, that's not more useful. Resonance can't happen over there. We are moving to elimination reaction. So what type of elimination reactions can happen? What are the types? Elimination reactions usually you see by in dehydration reactions or dehydrohalogenation reactions, right? So one small part will get eliminated in the presence of acid or base. So these are usually the transformation of saturated compounds to unsaturated compound. For example, it will happen like this. So if I'm having the alkane like this and presence of base, heat giving, so the product is unsaturated one. Okay, so it happens in the presence of acid or base, and also heat is also important in case of elimination reactions. So the examples are dehydration and dehydrohallucination. So what type of elimination can happen? The elimination is classified into two: E1 mechanism and E2. So what is the difference? First, let's talk about E1. Which is, as the name indicates, unimolecular. So what will happen? Carbocation formation will be there. So for example, I am taking a compound like this. The first step will always be carbocation formation. So leaving group leaves. Then this is a rate determining step. So that becomes the unimolecular reaction. Then the second step, base attack. So the base will attack this position, will take up the hydrogen. Due to that, the bond shift happens over there. The product is unsaturated one. In case of E2 mechanism, how it happens? So E2 mechanism, as the name indicates, that is a bimolecular mechanism. So that is a one-step mechanism. For example, here I am taking a compound like this. The base will immediately attacking. The shift will happen to another carbon, so that the transition state formation would be base attack to hydrogen. So hydrogen is about to leave. So this is our transition state. So finally it is forming a product like this, along with pH and X minus. So the rate depends on both base as well as the substrate reactant. That is about E1 and E2 mechanism. Then we are moving to addition reactions. In case of addition reaction, it happens, it's just opposite to elimination. So multiple bond system like unsaturated bonds will undergo addition reactions to form a saturated compound. For example, like this. We'll see more about addition reaction in hydrocarbons chapters as well, in upcoming chapters usually. So the addition reaction happens like this. In case of addition reaction, it is having two types: electrophilic addition reaction and nucleophilic addition reactions. Electrophile, once again, electron loving species. For let's say, instead of XY, I'm having Br2. So each Br will get occupied to one of those carbon. So for example, it will, the Br first attack electron rich, first attack the Br, so another Br will leaves the compound, forms a carbocation. Next, the eliminated one attacks the carbon so that the product will be like this. This is electrophilic addition reaction, but in case of nucleophilic, say for example I'm taking R C double bond O R dash, reacting it with nucleophile. The nucleophile first attack the compound so that the product goes via R dash. In case of nucleophilic addition, I'm taking an example of R C double bond O R dash. Nucleophile, along with that hydrogen is there. So nucleophile is electron rich. So this is attacking the carbon. So the product goes via O minus and then nucleophile with R dash. Further H plus is there. So this oxygen take up the H plus. The product is OH R dash. So this is a nucleophilic addition reactions. So today we dealt with substitution, addition and elimination reactions as well. If you have any doubt, please let me know. Please do more practice of questions. The next session we are going to deal with hydrocarbons, with alkanes, alkenes and alkynes, with other reaction mechanisms like what is Zaitsev rule, what is Markovnikov's rule, anti-Markovnikov and etc. Stay tuned. Thank you.